All right, so let's take a look at this system of equations. I'm going to, again, just write the augmented matrix for this system. So we have 1, 2, minus 3, negative 2. We have 3, minus 1, minus 2, and 1. And then we have 2, 3, minus 5, negative 3. All right, so let's see what we can do with this. Well, I have a 1 in the upper left-hand corner where I want it. So I'm going to use that 1 to zero out the columns below. That's the way I think I'll start. So I'm going to take row 2 and I'm going to subtract 3 times row 1. Okay, so let's do that first. I'm going to make little notes to myself. So this is minus 3. This is minus 6. This becomes a positive 9, and this becomes a positive 6. All right, so let's see what happens. I'm not going to touch row 1. I'm just going to leave it as it is. 1, 2, negative 3, negative 2. And then I'm going to add 3 times row 1, or negative 3 times row 1. So this becomes 0. This becomes minus 7. This becomes 7. And this becomes 7. Okay. Now I think at the same time I'm going to take care of row 3 as well. So I'm going to take row 3 and I'm going to subtract 2 times row 1. All right, so let's get rid of these little notations that I made to myself so I can create some new notes. All right, so if I take negative 2 times row 1, I get negative 2, negative 4. This becomes 6, and this becomes 4. All right, so what do we get? We're going to get a 0 here. We're going to get negative 1. And 6 plus a negative 5 is a positive 1. And then 4 minus 3 is a positive 1 again. All right, so I've got the first column taken care of. Now, let's see. It looks like an easy thing to do would just be to take negative 1/7 times row 2, right? That would get me a 1 in the center there where I want it. So I'm just going to leave row 1 as it is. 1, 2, negative 3, negative 2. And then this becomes 0, 1, negative 1, negative 1, right? All right. Now I think I can go ahead and just, I'm just going to go ahead and change the sign of the second row. I'm just going to take the opposite sign of row 3. So 0, 1, negative 1, negative 1. All right, you might see something happening there. So let's see. The next thing I want to do, let's see, I'll just put my little row operation here. I want zeros, right, above and below the 1 in the center. So let's see. One thing I might do is take row 1 and subtract 2 row 2, right? That'll give me a 0 in the second column. And so that gives me 0, sorry, 1, 0. See, this is negative 2. So this becomes negative 2. That becomes a 2. So this becomes a minus 1. And then this becomes negative 2. So this becomes a 0, right? 0. Okay. I'm going to leave the second row as it is. So 0, 1, negative 1, negative 1. And then, let's see, I'm just going to subtract at the same time. I'm going to take row 3 and I'm going to subtract row 2. Okay, that'll get the 0 below where I want it, below in the second column, below the middle there. So this becomes 0, this becomes 0, and this becomes 0. All right, so you can see right now I got this row of all zeros. And what am I going to do with that? Now there's not really much I can do to zero out this element right here in the first row, third column, because if I try to take row 2, then I end up messing up and I add it, or subtract it from row 1, then I end up messing up my 0 that I worked hard to get right here. Okay, so there's really nothing more I can do with this system. So I have to say, okay, what is this telling me? What is this telling me? Let's turn it back into equations. Let's take the augmented matrix and write the system of equations that corresponds to it. So the first row is telling me that x minus z is equal to 0. Okay, well, that could be true. The second row is telling me y minus z is equal to a -1. All right. And the last one is just telling me 0x plus 0y plus 0z equals 0, which is always true, right? That's always true, no matter what x, y, and z are. So there's no inconsistency there. So this is another case where we get an infinite number of solutions. All right. So what we're going to do is parameterize this solution. And I'm just going to say, let's let z be t. Okay, I'm going to use that as my parameter. And so then if I put that value of t in for z, then the first equation just becomes x equals t. And the second equation becomes y is equal to just adding, z to both sides. So, and then z is t, I end up with getting y is equal to t minus 1. Okay, so I can express this solution as x comma y comma z, right? Those are my values, is equal to t comma t minus 1, and then t, right? Z is t. So that's my solution. It's dependent on what t is, right? So we call this a dependent system of equations. It's dependent on t, right? So, but that's my solution. I get an infinite number of solutions depending on what t is. All right. Now we could choose a different parameter. So for example, let's say, so I'm just going to do an alternate solution just to show you that there's more than one parameterization for the same system. We could let y equals t, right? And then if we plug in y is t, then I get z is equal to, so I'm just using the second equation, is equal to y plus 1, which is t plus 1. Okay, and now I know z, and so I get x is also equal to t plus 1 if I just rearrange these equations. So another parameterization would be this, where we have t plus 1 comma t comma t plus 1 again. Okay, that's just an alternate way of parameterizing the same system. It's the same solution, it's just a different parameterization is all. All right, well, just to kind of summarize here, I just wanted, before I go here, I just wanted to look at these systems of when you have 3 equations and 3 unknowns. Those equations really represent planes, and there's different ways that these 3 planes could intersect. And so to sort of visualize what's happening here, you can see that if you have 3 planes that intersect like this, you get a unique solution, and your solution, unique solution, right? Then your unique solution is the place where all 3 planes intersect. Now you can also get the situation where the 3 planes intersect in a line, right? In these 2 situations here, right? Or they could all be the same plane. So either way, these give you an infinite, these sorts of systems give you an infinite number of solutions. Okay, if you wanted to visualize what that looks like. Now in these situations over here, you do not get a unique solution. In fact, you get no solution, right? You've got three parallel planes, or here you've got a case where you've got two are the same plane and the third one is parallel, or you get, they intersect in two different lines, but those lines don't ever intersect. In these two cases over here, basically you're getting intersections, but the intersections are all parallel to each other and you don't get a unique solution. So here, these are all situations where you get no solution. Okay? All right. So I will meet you in the next video.